We are almost everybody. So welcome everybody for the second day of ACTS. We will have the second lecture on Introduction to QCD and Small X Physics now with Sievert. Just a brief reminder to the online students. If you raise your hand, we give you the right to speak, and so you can ask the question. And if you turn on the camera, Matt can see also your face on the video, so on the TV. So please go ahead, don't be shy, also online, and ask questions. Excellent. It's to you.
Okay, good morning, folks. Is the audio coming through okay? Excellent. Okay, before I dive on in, I just wanted to point to how I'm uploading things on Indico. As yesterday very clearly illustrated, my guess of where one lecture ends and the next begins is not quite calibrated yet. So what I'm doing for now is I'm just continuing to upload all of the lectures as I go, and then I'll try and split them up separately into individual PDFs afterwards. So for now, for today, I've uploaded a combined lecture 1 through 3. You can again get that through the Indico page, and that now includes the stuff that we covered yesterday, which now has a section break where we actually stopped, and I'm going to continue trying to split things up as we go along. The other thing that I wanted to point out is in the full PDF versions of the notes, there's various other things that might be helpful for you, like these hyperlinks to appropriate sources for more information. So there's other things in here beyond what we actually get to cover on the board today. Okay. So let me go to the board and recap where we were last time. So last time I tried to sort of start at a very high level and orient us about how we're going to approach QCD. My goal is to derive or construct the QCD Lagrangian, hopefully within the next 2 hours or so, that tries to really explain what does it mean, where does it come from? What does it mean when we say that QCD is the gauge theory of SU3 symmetry? So last time we started off with sort of a you are here map of them all, saying if we're interested in QCD, QCD is a very unique non-abelian gauge theory. Gauge theories are a unique subset of interacting theories, and the entire framework that we're working with is a relativistic quantum field theory, which is the ideal marriage of relativity and quantum mechanics. Before diving into all of the details, we started off with a discussion about what one can and cannot learn from perturbation theory. Perturbation theory is great because it's a systematic expansion. Unlike, say, density functional theory, where you have the ability to calculate something, but you don't know how big your error is. Perturbation theory is sort of always controlled in this way. But it's not complete. There can be non-analytic functions, and we talked about an example last time, that simply don't have a Taylor series that we cover. They cannot be expanded. So if you work only in perturbation theory, you will never see such functions by construction. Even when perturbation theory is working, it doesn't necessarily converge, even though we often pretend that it does. So just working to higher and higher orders is not necessarily always a good idea. But perturbation theory can tell you how its degrees of freedom are evolving as long as they evolve slowly enough and they're not radically ruptured by a phase transition or something. This is what goes under the heading of resummation. And that is what we are aiming for ultimately as far as the low X side of things, to derive what is the resummation of low X physics and how does that change your cross sections. So then moving towards this discussion of gauge theory, the original sin, the problem of all of this is the existence of the scalar polarized mode for a vector field. Vector fields are allowed to have up to 4 polarizations, 3 space-like, 1 time-like, and that time-like polarization, since it's related to the metric tensor, comes in with a different minus sign than the space-like ones. So if the space-like polarizations are well-behaved, the time-like polarization is not, and that leads to negative definite quantum states, which is not compatible with any quantum theory, quantum states that live in the Hilbert space. And we talked about the way that a gauge theory elegantly solves this problem. If you have a massive vector boson, then I guess you can just get by with a constrained quantization, which is hard but doable. But a gauge theory solves this problem in a really beautiful way if the interaction of your vector field to anything else in the Lagrangian is of this very particular form, J dot A, where J is a conserved current. Then the transformation of A by shifting it with a scalar polarized mode is exactly equivalent to just adding a total derivative to the Lagrangian. And that's not an observable shift, right? That's a symmetry of the equations of motion. So this kind of interaction is very special. This one allows you to sweep this scalar polarization under the rug and turn it into an unobservable symmetry transformation instead. And so this is sort of the standard lore about gauge transformations being redundant degrees of freedom. That is not an accident, that is intentional to get rid of these scalar polarizations in the most effective way possible. So that was where we left off. So now let's talk a little bit more about what constructing this gauge structure actually does for our theory. So we started off with the free Dirac Lagrangian, which was for QED psi bar I d slash minus m psi. Here I only need one kind of fermion. We'll worry about multiple colors or multiple quantum numbers in a few minutes. So the free Dirac Lagrangian was this. We added a term of the form minus e psi bar gamma mu psi a mu to it, and that produced the, well, I don't know, let me call this the gauge Lagrangian for the moment. It's not completely QED because it doesn't have the kinetic term yet, but it does accomplish adding this special interaction form that renders this piece gauge invariant. So the addition of this extra term actually falls very nicely into the same structure as the free term that we had before. This d slash, as you recall, is just the contraction of the gamma matrices gamma mu with the partial derivative. If I've got the psi bar gamma mu psi here, that nicely combines with this structure. So this suggests that adding this extra term is almost like redefining the partial derivative. So if I just group these terms, everybody has a psi bar, everybody has a psi, everybody has a I gamma mu in this first term. And then the original Lagrangian we had has a partial derivative. And if I've got a minus sign here and I pull out an I, then I get plus I e a mu minus m psi. Very good. This object is, as I said, a modification of the partial derivative. This is referred to as the gauge covariant derivative. So this is capital D mu. And so the gauge Lagrangian, after adding this term, you can write it as just a mapping of the partial derivative to the covariant derivative. So in a very simple way, minimal coupling, the addition of this extra term of this form, can be thought of as just the replacement of the partial derivative by the covariant derivative, which introduces the vector field in exactly the right way that it produces this J dot A form. Okay, so what does this do for us? When we've added this particular form, now this effectively enlarges the symmetry group of our Lagrangian. We started off with the free Lagrangian, which was invariant under only global U1 transformations. Global U1, whereby global U1, I mean psi prime of x equals e to the I phi with phi a constant psi of x. And our purpose in adding in this extra term was to get rid of those scalar modes. But by adding this particular form, we've actually accomplished a lot more than that. We have effectively enlarged this symmetry. Now this combined Lagrangian is invariant under a local U1 transformation. The local U1 transformation effectively allows me to do a different phase rotation at every point in space. Psi prime of x is e to the I phi of x psi of x. So now phi of x is a field over space-time. . And that radically changes the structure of the transformation because now two different points in space can transform differently, arbitrarily differently. You can decide how you want them to transform, and they can be as different from each other as you want. And that sort of gets folded into this notion of the covariant derivative, because if different points in space-time transform independently of each other, then the notion of a derivative gets kind of messed up. You can't really compare 2 points that are close to each other in space because they could be very different in functional form. So that's essentially what's happening when we extend from this partial derivative to the covariant derivative.
Matt,
Sorry, sharing.
Oh, it's already sharing?
Yeah, we keep it sharing. That is the easiest way.
Oh, okay, great. So what happens to my Lagrangian under now this local transformation? My gauge Lagrangian was psi bar I d slash minus m psi minus e psi bar gamma mu psi a mu. So now if I transform the Lagrangian this way, L prime is psi bar prime I d slash minus m psi prime minus e psi bar prime gamma mu psi prime a prime mu. For the moment, I haven't decided at all what I'm going to do with a mu. You can imagine that I'm not transforming a mu at all, but let's just leave this free for the moment. All I'm going to do is transform psi. Just like before, this psi prime is just e to the minus I phi of x on this side, e to the plus I phi of x on this side, and the same thing over here. And at first glance, it doesn't seem any different from what we did before with the global symmetry, of course, because in the interaction vertex, this e to the I phi just exactly cancels that e to the minus I phi, and nothing special happens because they just multiply through to each other. Over here, however, something non-trivial happens. For the mass term, these guys cancel just like in the interaction term, but the derivative, however, changes the calculation, because the derivative, when this is a field over space-time, the derivative can act on the field as well as commuting past it to act on psi. So in addition to the piece where the derivative acts on psi and the phase just comes right through, I also have a new term. So I still have my original psi bar id slash minus m psi. I still get back the original vertex, psi bar gamma mu psi, a prime mu. But now I get something extra coming from the transformation of the free term. When the derivative acts on phi, I get an extra minus psi bar gamma mu psi d mu phi. And this is interesting, and it's no accident, right? This is precisely the conserved current J mu. This object is exactly of the form of a scalar polarized mode of the vector field. So this is exactly as if I've added a scalar polarized mode to the vector field itself. So this gives me back, let's say, let me just write it like this: e slash minus m psi minus e psi bar gamma mu psi, and now my shifted field is a prime mu plus 1 over e d mu phi. So what we've showed then is that we get back our original Lagrangian. It's basically this piece. If I didn't transform A, if I left A alone and I only did that shift, then this would be my original Lagrangian. And this is just a shift by a scalar polarized mode. And we showed last time that the coupling of this form, this extra term that you are adding here, is just a total derivative of the Lagrangian. Basically, I can take this derivative and pull it out past that conserved current, since d mu j mu is 0. And this extra piece is unphysical. It's just an overall total derivative to the Lagrangian. So the local U1 symmetry is equivalent to a shift by a scalar polarized mode. Meaning that this is unphysical or unobservable. And that's a good thing. So we set out to solve the problem of these scalar polarizations for the vector field. In the process, we've done something quite interesting. We've effectively enlarged the gauge group. We started off with a symmetry group only of global transformations. And by extending the Lagrangian to have this particular minimally coupled form, we've created a symmetry which is now a local U1 symmetry. If I want to make the Lagrangian completely invariant, not invariant up to a total derivative, then this tells me how I should transform A to compensate for that shift of gauge. So this tells me my A prime mu plus 1 over E d mu phi should be equal to my original A mu, which gives me the transformation law. A prime mu equals A mu minus 1 over E d mu phi. Make sure I didn't follow minus something. Yeah, I think that's correct. Okay, so this is what I mean when I say that we have now extended the symmetry. We've enlarged the symmetry transformations of the Lagrangian. The Lagrangian now sort of lives in a much larger space. It's a function not only of space-time, but it's a function of whatever your gauge condition is. These are all unphysical degrees of freedom. The solutions can look very different in different gauges, but the observables that they describe have to be the same. So essentially what this is doing is we've now combined the symmetry transformations of space-time with the symmetry transformations of the gauge sector. So I tried to illustrate this. This is what the picture looks like in my head. Let me imagine that I fix a particular gauge. Let me say I choose d mu a mu is 0, which is Lorentz gauge. In a particular gauge, I've got my full plane of space-time, 4-dimensional space-time. But I have the extra dimension as well of different gauges that I could choose. So just for the sake of illustration, let me imagine that this is a family of gauges, d mu a mu equals a constant, and that constant could be 0, 1, minus 1, whatever you like. Just so that there's an extra axis to my, my combined manifold. It's no longer just space-time. And even though the space-time behavior may be flat, we're not doing general relativity yet, the different gauge transformations of different points act a lot like a curved geometry. Right? So the fact that a point here may have a different gauge transformation from the point there can be thought of as the gauge dimension being curved in some sense. So this is a geometric interpretation of what we've done here. We've added in the extra gauge dimension, and with that extra dimension, the overall manifold isn't flat anymore. There can be curvature in the gauge direction, even though the spatial directions or the space-time directions may be flat. So this whole thing can be thought of very intuitively in terms of differential geometry on a curved manifold. And that gives a nice interpretation of what this covariant derivative is actually doing for us. Okay, so to summarize in words, basically what we have done is enlarge the symmetry group from global U1 to local U1. This effectively unites space-time plus gauge symmetry. And it can be thought of as a curved manifold. Thought of as curvature in the quote-unquote gauge direction. For the moment, this gauge direction is relatively simple. There's only one kind of gauge transformation that we can make, sort of. You can shift A by a scalar polarized mode, but there's no color degree of freedom yet, which we'll have in a little while. So it's not like you have 85 different types of gauge transformations you can make. There's really only one where you shift A by a scalar polarized mode. This, by the way, the combination of space-time and gauge symmetry is an essential feature of a massless vector boson. Essential for any massless vector boson. It's quite non-trivial to show, but Weinberg does a good job of it in his textbook. If you start with a massless vector boson, it is not invariant under Lorentz transformations. So a vector boson does not exist unless it is a gauge boson, because it cannot be squared with special relativity unless you get rid of those scalar polarized modes. So this is not just nice, this is mandatory for the photon to exist. So when we talk about a gauge theory, this is really what we need. This is the picture in my head. And now we're working on a much enlarged manifold where we've combined the space-time and gauge information into a single set of continuous symmetries. What that does for us is that now the covariant derivative this is effectively acting as a, let me call it parallel transports. Comparator. So I don't know how well my picture is going to come across, but what I have in mind is something like, I have some point in space-time, and at this point I have my field psi of x. Somewhere else in space-time I've got the point psi of x prime. These guys transform differently. So if I want to compare them, I can't just take the derivative, the partial derivative that takes the limit as x prime goes to x of psi of x prime minus psi of x divided by x prime minus x. This would be my ordinary partial derivative. If we're dealing with a curved manifold, like transporting vectors around a sphere, then the direction in a gauge sense here could have shifted because of the different gauge transformations over there. So, I don't know. Suppose that I make a gauge transformation where my gauge direction is, I don't want to say pointing in a given direction. Let's say I have d mu phi, d mu a nu is 0 over here. And maybe I have d mu a nu equals +1 over here, just for illustration's sake. The fact that the gauge direction can be different, that there can be some curvature in this non-space-time direction, means that this derivative is not well defined. It's not a good comparison. And the covariant derivative effectively subtracts off that difference. It's a lot like parallel transport around a sphere, where your vector going one way has to curve as you go around the equator. It doesn't stay pointing in the same direction. So there's a lot that one can say to make this differential geometry relation more concrete. Effectively, what you're doing is that your vector field A mu is a connection coefficient. I think it's called a metric connection. The old school name for this is a Christoffel symbol. But it exactly describes the fact that you may have curvature in the gauge direction as you take derivatives in the spatial direction. So how do I see what the covariant derivative is doing? The definition was the covariant derivative on my field psi of x was a regular partial derivative of psi plus 1 over e a mu of x psi of x. So I see this by asking, if I define this new derivative, how does that derivative change? If I have now derivative of psi at this point, and I compare it with the derivative of psi, I guess not at that point. What I want to do is I want to see how this thing changes under a gauge transformation. And I want to see that it transforms locally. So if I take this object, my d mu psi prime is then the regular derivative on the transformed field psi of x plus 1 over e a mu prime of x psi of x. So this transformation is, psi prime of x. So this is d mu plus 1 over e a prime mu of x acting on psi prime of x. And now I plug in what these things are. The 1 over e here, a mu of x. Oh, sorry. Sorry, I wrote the wrong expression here. I'm looking at the wrong line. Let me fix this. So the covariant derivative was d mu plus I e a mu. Sorry. So this is now d mu plus I e a mu prime of x psi prime of x. Now it should work out. I get d mu plus I e a mu of x. The transformation of a comes in with an extra minus I d mu phi of x. Yep. And then the transformation of psi is e to the I phi of x psi of x. And this extra term exactly compensates for the contribution that comes when this derivative acts on the scalar field up in that exponent. So this extra derivative gets canceled out. When I take this derivative, I get plus I d mu phi, which exactly cancels this one. And then so the only thing that's left is the part where the derivatives all act on psi, and this phase just harmlessly comes through. E to the I phi of x, d mu plus I e a mu psi, and this is just e to the I phi of x times the original covariant derivative d mu psi of x. And so you should compare this with the transformation of psi itself. Psi prime of x was e to the I phi of x psi of x. And what we see is that the covariant derivative now transforms in exactly the same way as the field itself. It's now a local transformation. And you see exactly that the extra piece that's been added to the covariant derivative is exactly the right thing that cancels the curvature, the changing of the gauge direction, if you like, from one point to another. So this is your parallel transport operator. This is the gauge covariant derivative that in a meaningful way allows you to compare how do I take a derivative in this direction at this point or at this point, even though the gauge structure may be different, and how do I compare derivatives in different directions? This is what's going to give us the field strength tensor. Okay, questions so far? Yes.
So you can transform the derivative and psi and a mu. Are these equivalent transformations, or are they doing different things?
They're all equivalent transformations. So the sort of original transformation that defines everything is this one. Once you define what the covariant derivative is, the covariant derivative will automatically do this for you by construction. And the transformation of A that we wrote down a moment ago also follows automatically from this definition. So I would say it's one transformation. These are all just different components of what that looks like. Okay. So the last piece that we need to complete the QED Lagrangian is the free kinetic term. And that requires defining the field strength tensor. This is F mu nu, which is just a generalized version of the curl. So compare this to, for instance, your intro physics relation that says that the magnetic field is the curl of the vector potential. This curl is just an anti-symmetric combination of derivatives. EI is epsilon ijk partial j ak. This is exactly the same structure. It's, let's say, the derivative along x of the y component minus the derivative along y of the x component. That's the curl. This is just the 4D version of that. The field strength tensor has a very simple relation in terms of the covariant derivative, which is powerful. This is the curl generalized to accommodate different space-time directions. That generalized curl doesn't yet take into account anything about the curvature of the gauge directions. So it should be, in some sense, a curl including the gauge directions. And since we know that the essential building block of a derivative is the covariant derivative, it's natural to ask, can I rewrite f mu in terms of the covariant derivative? Because the covariant derivative is the right object that takes into account the curvature in the gauge directions. The field strength tensor f mu is anti-symmetric by construction. So if I need an anti-symmetric combination of covariant derivatives, there's basically only one thing I can calculate, which is the commutator. Commutator of the covariant derivative d nu, acting on something for concreteness, let's say the field psi of x. This is an anti-symmetric object under mu goes to nu, and it has local gauge properties. So if I open up the brackets and calculate this, this is partial mu plus IE a mu, commutator with partial nu plus IE a nu acting on something like psi of x. The commutator of the partial derivatives is just 0. Because as long as you have a smooth function, it doesn't matter what order you take the partial derivatives. When the commutator involves the partial derivative and the vector field, you get an extra term, which comes from product rule, where the derivative acts on A instead of passing through to act on psi. Yes, sir?
Shouldn't the field strength tensor be independent of the gauge? Why
It is not necessarily. So the question is the field strength tensor independent of gauge? Yes, for the case of QED, no for the case of QCD, and we will see why. So for now, we're calculating this commutator. The first term just involving two partial derivatives is 0. The other terms, the cross terms, which involve partial derivative A and psi, pick up an extra term where the derivative acts on A. So I get plus IE d mu a nu times psi of x. The other term has d nu commutator with a mu, but in the opposite order. So that comes in with a minus sign. D nu a mu psi of x. And the last term is just minus e squared commutator of a mu with a nu times psi of x. And a mu is just a number. It's just a scalar quantity, if you like, one component at a time. So these two terms are 0. These two terms are non-zero, and they exactly reproduce what we started off with. So this combination is just the overall factor, i.e. partial mu a nu minus partial mu a mu psi of x, which is just i.e. f mu nu psi. So this is just equivalent to what we wrote down over there, but because this object has simple transformation properties in the gauge direction, this is a much better way of writing the same thing. So I can effectively define this as f mu nu defined to be minus I over E commutator of covariant derivatives. Yes. Okay, so for QED, this is a little bit of overkill, but for QCD, this is going to save us quite a lot of pain, because now we'll be able to define minimal coupling by the introduction of a covariant derivative. And then knowing the covariant derivative, we'll immediately be able to find the field strength tensor. When we go to QCD, the transformation laws of the gauge group are much more complicated. And this will immediately give us the corresponding transformation laws of f mu nu for whatever choice we make for the covariant derivatives. Okay, how am I doing on time so far?
You're still more than 25 minutes.
Okay, great. Okay. Maybe let me write down the Lagrangian one more time, and then we'll compare things before we shift over to actually discussing QCD.
I have a quick question as well.
Yes, sir.
I'm just trying to complete the analogy. I think of the regular covariant derivative as the generator of infinitesimal parallel transport. Spits out a vector that's like as close as parallel to the neighbor right before it.
Right.
So this gauge covariant derivative, is it generating an infinitesimal gauge transformation,
Yes.
or is it still parallel transport in space?
Yes, it's both of these things, right? So you're only taking the derivative in the space-like directions. You're not like taking a derivative in the gauge direction. But you're allowing for the fact that you can have different gauge transformations at different points, and the infinitesimal difference in gauge transformations is enough to capture that curvature.
Okay.
So it's really like that differential geometry picture of you're zooming into a small patch and comparing how differently does the gauge transformation here vary from the gauge transformation there. So I think it's both. Okay, so let me try to summarize what we've accomplished so far. The process for how we constructed QCD, constructing QED. QED and other gauge theories. So first step was starting with the free Lagrangian. We started off with L equals psi bar I d slash minus m psi. Second step is introduce a vector field by minimal coupling. We said we're going to add to this Lagrangian coupling of the form J dot A. And I guess in between this, before you know how to add this extra term, you need to know what is the conserved current. That by itself is non-trivial. Maybe I should have made it an extra step in between, right? This involves observing what global symmetries you have here. For those global symmetries, constructing the conserved current by looking at the variation of the Lagrangian. Once you know what J nu is, then you can add A nu to your Lagrangian in such a way that you eliminate the scalar polarization.
Quick question.
Yes, sir.
And by minimal coupling, you mean that we've defined the interaction term in Lagrangian by using only a conserved current?
That's right. By minimal coupling, I mean exactly this, using only a J dot A as your interaction vertex, where the J here is specifically the conserved current J that came from whatever global symmetries you started on. Okay, so once we've done this, this is now gauge invariant, right? This is now invariant under local transformations. This step, as we just saw, is equivalent to defining the covariant derivative. So equivalently, instead of saying I've added a term of this form, I could say I've defined this covariant derivative and I make the replacement d mu goes to big D mu. That's exactly the same as this. Once I've done this, I have a perfectly good gauge invariant theory, but A nu is not dynamic. There is no kinetic energy for this A mu, so you can't have any propagators for this Lagrangian. This would effectively describe, say, the interaction of a charged electric system with an external photon. If I have A mu external, then this provides the vertex that tells me how it interacts with electrons and positrons, but this does not include something like a propagator that allows two electrons to talk to each other. To have the propagator, you need the kinetic energy, and that's where we need the field strength tensor. So step 3 is construct the field strength tensor. F mu defined to be minus I over E commutator of covariant derivatives. And then once you have this, now you can add in the free kinetic term, or let's say the pure photon term. Which is minus 1/4 F mu F mu. And yes, so as was pointed out, the F mu itself is gauge invariant for the case of QED. It doesn't have to be in general. So if for QED, F mu is gauge invariant, so obviously F squared is also gauge invariant. And then this gives you the complete Lagrangian. This gives Lagrangian equals psi bar I capital D slash minus M psi minus 1/4 F mu F mu. Simple to write down, but there's an awful lot under the hood for where it comes from and why. And the only ingredient that you need, this is the part that's so profound. The only thing that you need to define QED entirely, all of Maxwell's equations, everything, is just this, or equivalently just this, or equivalently just this, U1 gauge symmetry. Once you tell me gauge theory of U1, then I immediately know that's this conserved current, that's this vertex, that's this covariant derivative, that's this Lagrangian. So there is a one-to-one mapping between your choice of the gauge group and all of the physics that comes from this. So this is the overall strategy, and this is what's still going to work for us when we construct QCD. The one change is that we're going to switch up this gauge group. We're going to introduce new quantum numbers called color. Doesn't really even matter how many there are, although for real QCD there are 3 of them. That larger gauge group is going to allow now for rotations, essentially, where you can scramble up which color you start off with and which color you end with in many different ways. And changing this gauge group propagates down and is going to ultimately give us uniquely the QCD Lagrangian for SU3 gauge symmetry. So as I sort of previewed yesterday, the essential difference when I changed the gauge group from being U1 to SU3 or SUN, it doesn't even really matter how many colors N you have. That essential difference is going from an abelian theory, a scalar theory, if you like, where there's no direction information to the gauge sector. So this is a, let me call it directionless gauge group. This is what I mean when I say that charge is a scalar. It doesn't have any direction associated with it, and because it doesn't have any direction, it doesn't matter what order you do gauge transformations in. It's exactly like the case of rotations in 3 or more dimensions. If I always transform around the same axis, always rotate around Z, you can do as many rotations as you want and the order doesn't change. It's perfectly abelian. It's only when you have multiple independent directions that don't play nicely with each other that you have real commutator algebra that knows about the algebra of rotations. So the change that's going to happen when we go to QCD is that we introduce the fact that there are multiple directions of gauge transformations that can all work independently of each other. And because there are multiple directions of the gauge transformations, it means that we've introduced a matrix degree of freedom, and these transformations don't commute with each other anymore. That non-commutative nature of the transformations is going to modify the conserved current a little bit. It's going to modify the covariant derivative a little bit. It's going to modify the field strength tensor a lot. And that transformation of the field strength tensor is going to introduce essential new effects for QCD. This is the piece that's going to give us the gluon self-interactions, which is the entire story for QCD. If all QCD was is take this vertex and put a color factor on it, QCD would be really boring. The essential part of QCD is the gluon self-interactions, which come entirely from that gauge piece. So that's where we're going to go next. Do I have enough time that I should start the construction of QCD now? Or should we take some questions instead?
I mean, if there are questions.
How much time do I have?
More than 15 minutes.
More than 15 minutes. So Okay,
I would take maybe questions.
okay.
And then we'll go from there. We can also split the 2 hours differently if you want.
Okay.
Yes.
We have the whole morning essentially.
Great. So yeah, why don't I pause here and ask if there's any questions or discussion that we want to have before we start repeating this process for QCD? Yes, sir.
Could you touch briefly on how this relates to the SU2 structure of the electroweak theory?
No, you just.
Oh, it's back, sorry. Yeah, absolutely. So we'll talk about that in detail in a few minutes, but very little changes if I work with a gauge group SU2 instead of SU3. The essential feature that gives us gluon self-interactions and all of this stuff is the fact that you have a matrix structure, SU something. Whether it's SU2 or SU3 only makes a tiny, tiny difference. And in fact, it's often advantageous to work in a general group SUN, and maybe even to consider certain simplifying limits of n. The thing that's maybe a bit different about the electroweak interaction is the fact that it breaks chiral symmetry, that it only couples to left-handed particles. So there's gamma 5s running around through the interaction vertex. It's not just J mu, it's more like J mu 5 or J mu minus J mu 5 so that you select only on the left-handed things. So as far as the gauge structure, I think it's extremely similar to QCD. You have the same kind of boson self-interactions in the electroweak theory, but it couples differently to the fermions because of the chiral symmetry. Yes.
Can I ask you?
Sure.
Okay, so the first one is, so there's one choice that you can make for the gauge group for each QED, is that right?
I said that, but it's a little bit misleading. I wanted to illustrate the fact that there's not multiple independent types of gauge transformations that you can make in the sense of many different generators of the gauge transformations. There's only one generator of the gauge transformation if you want. So all the gauge transformations are of this form, but your phi of x can be anything you want. So it's misleading for me to say there's only one kind because your phi of x could be as simple or as complicated as you choose it to be. But it's always of this form. And I'm comparing that, we'll show this again in a minute, for the case if phi was a vector, let's call it in some space. So we're familiar with this for the case of the rotation generators, where you have the angular momentum operators up here, and you have a series of rotation angles that could be many phis. What I mean here is that there is only one phi. Phi could be a field over x, but there's only one of them. Here I can have many phis, and that's a much larger symmetry group because now I can rotate among the different components of these vectors. That's what I mean. Sure. And the second one?
So I don't know, maybe it's a separate class without this question, but what would it look like to add a photon self-interaction? Do you have to like do another gauge transformation or like?
You mean in QED, literally a photon?
Yeah, photon interaction with photon.
You cannot add a photon self-interaction to QED without breaking gauging variance. That's exactly the statement that was asked before about FU being gauging variance. So the self-interactions, as we'll see for gluons, come in here. It looks like not just d nu a nu minus d nu a nu, but you also get something which is plus g f a b c a nu b a nu c, where now these guys have extra color in this. So there is an interaction that gets created, which is in fact demanded by gauging variance if you have a non-abelian theory. This FABC comes from the commutator of the matrices. So if I choose a non-abelian theory, then the commutators of the matrices must appear here, and they must add a boson self-interaction to the theory. Conversely, if I have an abelian theory, this thing is strictly gauge invariant by itself, and I cannot add something like this without breaking the U1 gauge invariance. So I would say, no, you cannot have a photon self-interaction in QED, period, because of the U1 gauge symmetry of QED. If you pick a more complicated gauge group, we'll talk about this as well, you could, for QCD, right, QCD is the gauge group SU3. SU3 contains the 8 gluons, which are all charged. A very, very closely related group is U3, which doesn't have that special constraint. This has 9 gluons, if you like. It contains the same 8 that you had before, plus something proportional to the identity matrix. That identity matrix is a vector boson, which is neutral. It carries no charge of itself, so you might call it a photon. So there is a natural way to include something that looks like a photon in a theory that has boson self-interactions, but it's still the identity matrix. This is still the abelian subgroup. So this would still be a non-interacting photon piece of a U1, a U3 gauge theory. So maybe that's more information than you're asking for. I think the answer is in QED, no, you can't have a self-interaction. Photons in non-abelian theories are possible. Any other questions at this point? Cool. By the way, the procedure that I just wrote on the board, in my mind, this is the general procedure of particle physics. You can use this to invent any gauge theory that you want. Basically, all you have to do is make an experimental observation or make a guess. So you observe, hey, I watched an up quark transform to a down quark. How do I make a gauge theory that does that? Well, I put the up quark and the down quark in a matrix, and I ask, what kind of rotation could I have that transforms these guys among each other? If I observe experimentally that some process transformed up into down quarks, then I invent the matrix that does it. I take a wild guess at the group. I might take, for instance, SU2 if I see a rotation among the two flavors of quarks here. And then I would take it and run with it. I would construct the Lagrangian of a gauged SU2 interaction. And this is essentially how you would end up with the electroweak force. Modulo this question about chiral symmetry breaking, where it's really only the left-handed pieces of the fields. So you have to work a little bit harder. So this is your general prescription for particle physics. Take particles that interact with each other, stuff them into a matrix, take your best guess at what kind of group might relate them to each other, calculate, and then compare with data. So you would do the same process if you want to construct your favorite grand unified theory. Yes, sir.
So the bosons are the mediators of the force between the
Yes.
particles, right? Now you said U3 has photons as well as gluons.
Yes.
So
One photon. Yes.
So does the photon also act as a mediator?
Yes, absolutely. So all 9 of those bosons are the force carriers, if you like, of U3 gauge symmetry. The photon is only different from the gluons in that case because the photon is proportional to the identity matrix, so it commutes with everything. It's the abelian subgroup of U3.